Olá pessoal, estamos de volta com o curso de Java básico, essa é a aula de número 35 e hoje nós vamos falar sobre recursividade. A agenda para a aula de hoje então é aprender como criar métodos recursivos e nós vamos utilizar como exemplo como calcular o fatorial de um número, que foi um exercício que nós resolvemos na aula.
Oi, CDF! Seja bem-vindo ao Dicionário do Programador do Código Fonte TV.
A cada vídeo, um termo,
Uma tecnologia
ou uma palavra utilizada por todos nós neste maravilhoso mundo da programação. Recursividade.
Contextualizando, a recursividade está intimamente ligada na matemática. mas também nas linguagens de programação e é muito utilizada no desenvolvimento de sistemas.
Embora a recursividade tenha um conceito muito simples, ela normalmente faz com que programadores, principalmente os de primeira viagem aí, deem um certo nó no cérebro.
A definição é simples e seu próprio nome já diz tudo. Na matemática se utiliza muito o termo de definição indutiva. Mas aqui no nosso mundo, a recursividade pode ser muito bem definida como um objeto que se define em termos de si próprio.
Ou, mais simplificado ainda, é utilizar uma função que chama ela mesmo até a sua resolução.
E a ideia principal em se usar a recursividade é justamente dividir a resolução de um problema grande através da resolução de vários probleminhas.
Ok, então vamos lá. Eu tenho uma função que chama ela mesma, que depois chama ela mesma, que por sua vez chama...
is a way of solving a problem by having a function call itself. To see how that works exactly, let's take a look at a few examples here. First of all, let's think about factorials. And let's just quickly review factorials here. If you're given a positive integer n factorial is equal to n times n minus 1 times n minus 2 times and so on, down to 3 times 2 times 1. So I'm just going to give you a few examples here. 4 factorial is equal to 4 times 3 times 2 times 1, which is equal to 24. And 2 factorial is equal to 2 times 1, which is 2. And 1 factorial is 1. And what about 0 factorial? It's actually defined to be 1. And you might say, why is that? But basically that's just how it's defined. And let's just say here, we're trying to write a function called, let's say, fact, which takes a positive integer, or 0, as its argument, and returns the nth factorial. And let's say we want to write this function using recursion. How can we do that? To solve this problem, or to write this function recursively, we need to actually examine this equation in a little bit more detail. Okay, so I brought that equation over here, and like we saw earlier, we had n factorial being equal to n times n minus 1 times n minus 2, and so on, times 3 times 2 times 1. And when you see this equation, and when you look at this part following the first n, you might notice that this part is equivalent to n minus 1 factorial. And that might be more obvious if I write it separately here, as n minus 1 factorial equals n minus 1 times n minus 2 times and so on, times 3 times 2 times 1. So this whole thing is equivalent to this part. So you might say, well, we can rewrite n factorial as n times n minus 1 factorial. And that's good. This new equation is mostly correct. But it's not a complete definition of factorials. Let's see why. Let's say if you plug in 2 to n right here, it works just fine because you'll get 2 factorial being equal to 2 times 2 minus 1 factorial, which is 1 factorial. And 1 factorial is 1, so 2 times 1 factorial is 2, and that's correct. What if you plug in 1 here? It's still good because you'll get 1 factorial being equal to 1 times 1 minus 1 factorial, which is 0 factorial. And 0 factorial is 1 as we saw earlier, so that's 1. And this is correct. But as soon as you plug in 0 here, it breaks. Let's see how that works. 0 factorial is equal to 0 here, right here. Times 0 minus 1 factorial, which is minus 1 factorial, and minus 1 factorial is not defined. So this definition works only for n that is greater than or equal to 1, but it doesn't work for 0. So actually, for this definition to be complete for factorials, we need to write n factorial as 2 separate cases. So here we're going to write n factorial is equal to n times n minus 1 factorial if n is greater than or equal to 1. And if that's not the case, or if n is equal to 0, I wrote otherwise here, n factorial is equal to 1. And this is actually a complete definition of all factorials for all positive integers and 0. So let's just quickly see how we can use this new definition of factorials to find the factorial of any positive integer. Let's say 3. So if you ask yourself, what's 3 factorial? There are 2 ways of answering that question. The first one would be to use the old definition, and then the second way would be to use this new definition. And let's use this new definition here, because we're going to use this new definition later to write a function using recursion as well. So using this definition, we can ask ourselves, what's 3 factorial? Well, 3 is greater than or equal to 1. So by definition, this is equal to 3 times 3 minus 1 factorial, which is 2 factorial. And then we can ask ourselves, what's 2 factorial? By definition, since 2 is still greater than or equal to 1, it's equal to 2 times 1 factorial, and then we can do the same thing for 1. What's 1 factorial? Well, it's 1 times 0 factorial. And then as soon as we have this, we'll know that 0 factorial is 1 by definition. And as soon as you have that, you can plug 1 to 0 factorial here, and then you'll know that 1 factorial is equal to 1 times 1, which is 1. And then you can plug that back in here, and then you say, okay, 2 factorial is 2 times 1, which is 2, so we can plug that back in here. And then we'll say 3 factorial is 3 times 2 factorial, which is 2. So the answer here is 3 factorial is 3 times 2, which is 6. Okay, now this whole process might seem a little bit silly, but this kind of thinking is going to be actually the basis for implementing the function we wanted to implement earlier, recursively, fact of n. And fact of n, as I said earlier, is going to take n, which is either a positive integer or 0, and it's going to return n factorial. So let's see how we can implement it using recursion. And actually, all you need to do for that is you need to translate this new definition of factorials into code. So let's just bring this definition up here. So like we saw earlier, n factorial is equal to n times n minus 1 factorial if n is greater than or equal to 1, and then it's 1 otherwise, or if n is equal to 0. And then we're going to translate this definition directly into code, and I'm going to use Java here just as an example. And like we saw earlier, we're trying to write a function called fact, which is going to take n, an integer, and it's going to return an integer, which is going to be n factorial. And just for simplicity here, I'm going to assume that the given n is always positive or 0, so it's never negative. And to write the rest of the function, it's pretty simple. We just need to translate this formal definition into code. So here it says n factorial is equal to n times n minus 1 factorial if n is greater than or equal to 1. And what we're going to return from this function is going to be the value of n factorial. So here we just need to write if n is greater than or equal to 1, we're going to return n times fact of n minus 1. So this is the same as saying the value of factorial n is going to be n times factorial of n minus 1 if n is greater than or equal to 1. And then we're going to write otherwise or else. That's when n is equal to 0. We're just going to return 1 because we know that that's the value of 0 factorial. So as you can see, this is a recursive function because this calls itself fact calls itself right here to solve the problem of finding n factorial. Okay, this function seems pretty simple, but does it actually work? Well, it does. To see how, let's take a look at a few examples here. If you have fact of 0, I just wrote it as f of 0. That's pretty easy because here we get this line right here because 0 is not greater than or equal to 1. So we're just going to return 1, which is correct because 1 is 0 factorial. And what if you're given 1 as n? Then I'm just going to write f of 1 here to stand for fact of 1. When this is called, it's going to hit this line right here because n is equal to 1. And then it's going to try to return 1 times fact of 1 minus 1, which is 0. So f of 0 here. And then when f of 0 is called, it's going to go to this right here that we saw earlier. And then f of 0 will say, okay, my value is 1. So this is going to return 1. And then in f of 1, it's going to say, okay, what I'm going to return is 1 times the value of fact of 0, which is 1. So we're going to return 1 times 1, which is 1. So that's the correct answer. Okay, to help you understand this a little bit better, I'm going to give you another example here. Let's say fact of 4 is called. I'm just going to write f of 4 here. And when it's called, we go to this line right here. And since n, which is 4, is greater than or equal to 1, it's going to say what I want to return from that function is 4 times fact of 3. But we don't know what the value of fact of 3 should be, so we need to call that function. So I just wrote it here. Here I'm saying the value of f of 4, the return value of f of 4 will be 4 times f of 3. And then we need to call f of 3 to find the return value for that. And once we call f of 3, the same thing will happen. The return value of f of 3 will be 3 times f of 2, whatever the return value of f of 2 is. So we'll call f of 2 or fact of 2. And then we'll say, okay, that's 2 times f of 1. Actually, there's a typo here, whatever the return value of f of 1 is. So we'll call f of 1, and then f of 1 is 1 times f of 0. And then as soon as we call f of 0, we go to this line like we saw earlier. So we'll just return 1 from that. Once we return 1 from f of 0, we'll go back to this call, f of 1. And then we'll say, okay, we wanted to return 1 times f of 0. And we now know the value of f of 0, which is 1. So we'll just say we're going to return 1 times 1, which is 1 from this function. And then we'll go back to this call where n was 2. And we wanted to return 2 times f of 1, whatever the return value of f of 1 was, and that turns out to be 1. So we'll return 2 times 1, which is 2 from this function. And then we'll just basically keep doing that. F of 3 wanted to return 3 times f of 2, and f of 2 happens to be 2 here. So we'll return 6 right here, and then we'll go back here, the original call that we made, and then f of 3 turns out to be 6. So we'll say, okay, f of 4, we wanted to return 4 times whatever the return value of f of 3, which turns out to be 6. So we'll return 24 from this function, which is correct. And this wraps up this section about factorials. Let me know in a comment below if anything was unclear. Okay, now to better understand recursion, let's take a look at another example here, the Fibonacci sequence. So I already talked about this in one of my previous videos, but the Fibonacci sequence is a sequence of numbers that starts with 2 ones at the beginning, and the numbers after that are generated by adding up the 2 previous numbers. So for example, the third number is 2 because 1 plus 1 equals 2, and then the fourth number is 3 because 1 plus 2 equals 3, and so on, and it just keeps on going forever. And given this sequence, let's just say that we're trying to solve the problem of writing a function, let's say fib, which takes a positive integer n, and returns the nth number in this sequence, the nth Fibonacci number. So if you're given 3 as n in this function, you should be able to find and return the third Fibonacci number, which is 2, and if you're given one formally defined relation between 2. So I'm denoting the n would be the sum of equation is as soon as you Fibonacci f minus 2 minus 2 when into and n is a positive integer. So we had a few examples here.